Good morning, students. Welcome to this ninth session on Introduction and Analysis of Plane Trusses for the subject Analysis of Determinate Structures. And myself, Vahini M of Government Engineering College, Haveri. So, in the last session, we have discussed about the concept of influence lines, how to draw the influence line diagram, and then we have drawn influence line diagram for a simply supported beam. Okay, assuming a unit load. Okay, we have drawn influence line diagram for reaction, shear force, as well as for bending moment for a simply supported beam. And in this session, we'll take up or we will apply the influence line diagram. We'll find the application of influence line diagram for the analysis of a simply supported beam. Okay, so that means in this session we'll be applying the influence line diagram to find the reaction, shear force and bending moment for a simply supported beam subjected to point load or concentrated load, a UDL longer than the span and UDL shorter than the span. Okay, so these are the three cases which can occur on a beam. Okay, let us take up the first example on point load. Okay, so determine the reactions, shear force and bending moment at 6 meter from left end for the beam shown in figure. Okay, so this is the beam. AB is a beam wherein a 80 kilonewton, a point load of 80 kilonewton is acting at 6 meter from end A. Okay, so where we have to find shear force and bending moment as well. So let us take that point as C. So here the point of application of load as well as the point of reference both are same. Okay, the span of the beam is 15 meter. So next we'll find how to find the reactions. So this is the given problem. Okay, so we have already plotted the shear force influence line diagram for reactions. Let us apply that concept over here to find the reactions for numerical problems. Okay, so this is the influence line diagram for reaction RA. Okay, so RA will be equal to when the unit load is equal to 1 and it will be acting at A, and it will be 0 when the unit load is acting at B. Okay, so when it moves from A to B, at point A when the unit load is acting at A, reaction will be maximum, hence it is equal to 1. When the unit load is acting at B, RA will be equal to 0. So this is the variation of ILD for RA. Okay, so since the load in this case is at point C, okay, so this 80 kilonewton is acting at C. Okay, so we have to find this ordinate. Okay, so let us plot this line. So how to find this ordinate? Okay, by applying similar triangle principle. Okay, so from similar triangle principle we can find this ordinate. Let us apply that one. 1 divided by this span is 15 meter. 1 divided by 15, that is equal to this ordinate y divided by, what is this remaining length? If this is 6 meter, what is this remaining length? This is 9 meter. So y divided by 9. Hence y will be equal to 0.6 meter. So this ordinate is equal to 0.6 meter. Okay, so now to find a reaction at A, that is RA, that is obtained by magnitude of the load into ILD ordinate. So this magnitude is 80 and the ILD ordinate at the reference point is 0.6. So therefore reaction at A will be equal to 80 into 0.6, that is equal to 48 kilonewton. Okay, but maximum reaction will occur when this 80 kilonewton will act at point A. Okay, that will be exactly equal to 80 into 1 will be 80 kilonewton only. But as the load moves from A to B at C, when the load is at C, the reaction at A will be equal to 80 into this ordinate is 0.6, that is equal to 48 kilonewton. Okay. Next we will draw the influence line diagram for RB to find reaction at B. This is the influence line diagram for RB. So highest ordinate of 1 is at B. Okay, and 0 at A. Similarly, as the load is at C, we will find this ordinate by using similar triangle principle. Same thing, sum from similar triangle principle. 1 divided by 15 is equal to y. This is y divided by this length. You have to take this length. This is the triangle. Okay. So this length is 6 meter. So y by 6. Hence y will be equal to 0.4. 0.4, you can take it as meter, anything, 0.4. Okay. So this ordinate will be equal to 0.4. Hence reaction at B is equal to magnitude of load into ILD ordinate. So magnitude is 80 and ILD ordinate is 0.4. Hence reaction at B will be equal to 32 kilonewton. Okay. As a cross check, you can apply sigma MA is equal to 0 so that you can obtain RB, and then you can cross check with the values what you have obtained using ILD. Okay. So this is how you are going to apply influence line diagram to a numerical example. Okay, using this the standard ILD, will be obtaining the ordinates at the required ordinates, and we will just multiply the magnitude of the load into ILD ordinate. Okay, so that is how the reactions will be formed. Okay, so next we'll go for finding the shear force. So this is the given example. Okay, so shear force will be the same thing what we have plotted in the last problem or in the last session. So this will represent RA and this will represent RB. Okay, so we have to find the ordinates at join at the point C. Okay, so let us take this as the ordinates. Okay, so same thing, by applying similar triangle principle, let us find these ordinates, positive ordinate and negative ordinate. This is 1 by 15. Same thing what we have found in the previous slide. 1 by 15 is equal to y by 9. This one, y by 9, that will be equal to y is equal to 0.6. So this ordinate will be equal to 0.6. And for this, to find this ordinate, 1 by 15 divided by is equal to y by 6. 6 meter is this length, y by 6. So hence y will be equal to 0.4. So this ordinate is 0.4. So now to find shear force at C. Okay, so at C there will be positive as well as negative shear force. Okay, so first let us find the negative shear force. So this ordinate is 0.4. To find negative shear force, magnitude of the load into ILD ordinate, that is negative ILD ordinate. Okay, so this is the negative ILD ordinate. So let us substitute that one. 80 into negative ILD ordinate is 0.4. So 80 into 0.4 is 32 kilonewton. So negative shear force at C is minus 32. Since you have already mentioned it as negative, therefore I have not represented it as minus here. Okay, so that is 32 kilonewton. Next, to find the positive shear force at C, same thing, magnitude of load into positive ILD ordinate. Okay, so let us substitute positive ILD ordinate is 0.6 into magnitude is 80. So if you substitute and find, you will get a positive shear force of 48 kilonewton at this point C. Okay, so now if you draw the influence line diagram, so this will be the influence line diagram for shear force at C. Okay, so these are the extension. Okay, you no need to represent this one, just for your reference you can draw like this, but this is what ultimately you have to show, ILD for shear force at C. Okay, next we'll find the bending moment at C. So this is the given problem. So we know that bending moment at any point on the beam is ILD, ordinate of ILD at C is given by AB by L, where A is 6 meter and B is 9 meter divided by 15, L is 15. So that will be equal to 3.6. Okay, so therefore this ordinate is equal to 3.6. AB by L is equal to 3.6. Okay, so that is the ILD for bending moment at C. Now we will apply this to this equation. Bending moment at C is equal to magnitude of load into ILD ordinate. So this equation will remain same whether you find a reaction, shear force or bending moment. So this will be same, only the ordinates will get changed. Okay. So magnitude of load is 80 and ILD ordinate is 3.6, that will be equal to 288 kilonewton meter. 288 kilonewton meter. Therefore bending moment at C is equal to 288 kilonewton meter. Okay. So that is the first problem. This is how you are going to apply the influence line diagram for a unit load for a given magnitude of load. Okay. Next we move to the next example of simply supported beam subjected to UDL longer than the span. Okay. So this is the problem. A UDL of intensity 30 kilonewton per meter longer than the span crosses a girder of span 20 meter from left to right. Calculate the reactions, shear force and bending moment at a section 8 meter from A. So let us draw this one. AB is the simply supported beam of 20 meter span. Okay. It carries a UDL of 30 kilonewton per meter, which is longer than this 20 meter. Okay. And we have to find shear force and bending moment at 8 meter from end A. So let us take this point as C. Okay. So next we'll apply it to find reactions. This is the given problem. UDL longer than the span, so it will be crossing both A and B. Okay, so that means UDL throughout its length. Okay, it's a case of UDL throughout its length. So to draw the or to find the reactions, we have to plot the influence line diagram for RA. To find reaction at A, plot the ILD for RA. This is the ILD for RA. Okay. So since in the last problem there was a point load, we used to find the ordinate under the point load. Whereas here the UDL is acting throughout the length. Okay, so therefore in such cases how to find reaction at A means RA is equal to magnitude of load into area of ILD under the load. So we have to find the total area under this load. Okay, because UDL is acting throughout its length, therefore you have to consider the total area of this ILD. Okay, so this is the area. Let us substitute it. RA magnitude is 30, that is intensity is 30 into, it's a triangular area. Okay, half into base is 20 meters and height is 1. Okay, half into base into height. So that will be equal to 300 kilonewton. Okay. And then to find RB, let us draw the influence line diagram for RB. Okay. Since UDL is acting throughout, so RB is obtained by magnitude of load into area of ILD under the load. So we have to consider the total area of the ILD because UDL is acting throughout the length. Substitute, we'll get the same answer. 30 is intensity, half into base is 20 and height is 1. So half into 20 into 1 into 30, that will be equal to 300 kilonewton, which is exactly equal to WL by 2. Okay, when the UDL is acting throughout its length, reaction at both ends will be equal to WL by 2. W is 30, L is 20. W into L will be 600 divided by 2 will be 300. Same thing. Okay, so whether you calculate it from normal statics principles or by applying influence line diagram, you will get the same answer. Okay, next we'll find the shear force at this point C. So UDL is acting throughout the length. Okay, so this is the shear force ILD for shear force RA RB. If you combine both, you will get ILD for shear force. Okay, so at C, to obtain a shear force at C, let us plot the ordinates at C. Okay, positive and negative ordinates. Same thing, by using similar triangle principles, we'll obtain the positive and negative ordinates. So 1 by 20, that is equal to y by 12. So this length, we are taking this positive ordinate. So 20 and this is 8. If this is 8, the remaining length will be 12 meter. Therefore, 1 divided by 20, that is equal to y divided by 12. Therefore, y is equal to 0.6 meter. So this ordinate will be equal to 0.6. Similarly, the negative ordinate will be equal to 1 by 20 is equal to, let us take this as y divided by 8, y by 8. So from which again you will obtain y value as 0.4. So this ordinate will be equal to 0.4. Now to find shear force at C, that is negative shear force at C is equal to equals magnitude of load into negative area of ILD under the load. Okay, so magnitude is, that is intensity is 30 into negative area of ILD under the load. So this is the negative area. This is the negative area under the load. Negative area of ILD under the UDL. Okay. Therefore, let us substitute it. Negative shear force is equal to 30 is the intensity into area of this ILD is half into base is 8 meter and height is 0.4 meter. Therefore, that will be equal to 48 kilonewton. So, negative shear force at C will be equal to minus 48 kilonewton. Okay. Next, to find positive shear force at C, same equation, magnitude of load into positive area of ILD under the UDL. Okay. So, this is the positive area under the UDL. Okay. You can ask why we have to consider this area, why we can't take this area. Okay, as UDL is acting throughout this length as well. Okay, when we have to find when the load is in between AC, we will be considering the right portion. Okay, so wherein we have to consider RB, negative RB minus RB. Therefore, the load will be in between AC. To obtain negative shear force, the load will be in between AC. Therefore, we have to consider this area of UDL. Okay, and when the load is in between BC, you will get positive shear force. Okay, to obtain positive shear force, that is we have applied RA. Okay, will be coming from left to right. Okay, when we are coming from right to left, this is minus RB that we have explained in the last session. Okay, so when the load is in between BC, we will be considering RA. Okay, so when the load is in between BC, we have to consider this area, not this one. Okay, that you have to keep it in mind. So this is the variation of shear force at C. Okay, so let us substitute. 30 is the intensity, half into base is 12 meter and height is 0.6. So that will be equal to 108 kilonewton. So positive shear force at C is 108 kilonewton and negative shear force at C is 48 kilonewton. Okay, so this is the variation of shear force or influence line diagram for shear force at C. Okay. Next, we'll move to find bending moment. So this is the given problem and the loading is longer than the span, hence it is acting throughout its length. Okay. So to find bending moment, let us draw the ILD for bending moment. We have to find bending moment at C. So let us plot it like this. This is the ILD for bending moment. Okay. So this ordinate is equal to, ordinate of ILD at C is equal to AB by L. Okay, A is 8 meter, B is 12 meter, that whole thing divided by 20. AB by L is 8 into 12 divided by 20, that will be equal to 4.8. So this ordinate is equal to 4.8. Okay. Next, we'll apply it to this equation. Bending moment at C is equal to magnitude of load into area of ILD under the UDL. Okay, so as UDL is covering throughout the length, we have to consider the total area. Okay, magnitude is 30 and area is half into base is 20 meter and height is 4.8. So that will be equal to, bending moment at C is equal to 1440 kilonewton meter. So this is the ILD for bending moment at C. So that is how we will calculate reaction, shear force and bending moment for a simply supported beam subjected to UDL longer than the span. Okay. Next we will take up an example on UDL shorter than the span. Okay. A UDL of intensity 50 kilonewton per meter and of length 7 meter is rolling over a simply supported girder of span 20 meter. Calculate the reactions, shear force and bending moment at a section 7 meter from A. So this is the given problem wherein the simply supported beam AB of length 20 meter is subjected to a partial UDL of 7 meter whose intensity is 50 kilonewton per meter. It rolls from A to B, but for this instance it is acting at A to C. Okay. So for this case, we'll find the reactions, shear force and bending moment. Okay. To find reactions, let us draw the given problem. Okay. And reaction at A is obtained by drawing the influence line diagram for RA. Okay. RA is given by magnitude of load into area of ILD under the load. Okay, so what is the area under this load? This is the area, hatched portion is the area that is covered by this UDL for this ILD. Okay, now we have to find this area. Okay, so to find this area we need this ordinate. How to get these ordinates? Again using the similar triangle principle. Okay, so from similar triangle principle, 1 by 20, 1 divided by 20 is equal to y divided by this remaining length 13. Okay, if this is 7, so this will be 13. Therefore y is equal to 0.65 meters. So this ordinate will be equal to 0.65. Okay, let us substitute it. RA is equal to, so we can divide this hatched portion into two area. One is triangle and the other one is a rectangle. So magnitude of load is 50, that is intensity, into area, this is area of triangle, half into base is 7 meter and height, this total height is 1 meter, in which if you deduct 0.65 you will get this height of triangle as 0.35. Okay, so therefore half into 7 into 0.35 plus, let us take area of this rectangle, 0.65 is the depth and width will be 7 meters. So 0.65 into 7. So this whole thing you should multiply with 50. You add the areas and then multiply with the intensity of UDL. Okay. So from which we will obtain the reaction at A as 288.75 kilonewton. Okay. Next, to find reaction at B, let us draw influence line diagram for RB. Okay. Again same thing, RB is obtained by magnitude of load into area under the load. So let us hatch the portion under the loading. Okay, so this is the area covered by ILD under the load. So let us find this ordinate by using similar triangle principle. Same thing, 1 divided by 20 is equal to y divided by 7. So that gives a y value of 0.35. So this ordinate will be equal to 0.35. Okay, you can observe if you add these two you should get 1. Whether it is in reaction, in shear force, okay, in both the cases if you add these two you should get 1. Okay, let us substitute here. So magnitude is 50, area only a triangle, half into base is 7 meter and height is 0.35. So that gives a reaction at B as 61.25 kilonewton. So that is how we have to apply the influence line diagram to find reactions when the UDL is shorter than the span. The position may vary. It may be, for this instance it is at C, it may be from C to some 7 length. From C it may be acting for a 7 length or 7 meter from end B, like that. The position of UDL may change, but the concept will remain same. This is what you have to understand. Whenever a UDL is acting, you just take the hatched area and then multiply with the intensity of UDL to get reaction or shear force or bending moment. Okay. Next, to find shear force, this is the given problem. Okay, and this is a shear force, ILD for shear force. Okay, at C we have to find shear force, therefore mark the ordinates. Let us find the ordinates, positive and negative ordinates, by using similar triangle principles. So this ordinate, positive ordinate is equal to 0.65 and negative ordinate is equal to 0.35. So this is 65 and this ordinate is 0.35. Okay. We know that negative shear force is equal to magnitude of load into negative area of ILD under the load. So negative area is only this much. Okay. So therefore magnitude is 50 into area is half into base is 7 and height is 0.35. So that gives a negative shear force of 61.25 kilonewton. 61.25 kilonewton. Okay. And what is the positive shear force here? Positive shear force means UDL should be in between BC. But for this case, the UDL is not acting in the right portion, it is in the left portion. Okay, so therefore the hatched area will be 0. Area under the UDL will be 0. Therefore, positive shear force at C will be equal to 0. Hence, this is the only variation of ILD for shear force at C. Okay. Next, we'll find it for the bending moment. The given problem is like this. Okay. This is the ILD for bending moment at any point. This is, we need bending moment at C. Therefore, we have to find this ordinate by applying similar triangle principle. So, ordinate of ILD at C is equal to AB by L, not by applying similar triangle principle. We have this formula as AB by L. So A is 7 meter, B is 13 meter divided by 20. So that will be equal to 4.55. So this ordinate is 4.55. Let us substitute here. Okay. So we know that bending moment at C is equal to magnitude of load into area of ILD under the UDL. So let us hatch that portion. So this is the only portion which is covered by the UDL. Okay. So therefore bending moment at C is equal to, intensity is 50. Area of this hatched portion is half into base is 7 meter and height is 4.55. So that will be equal to 796.25 kilonewton meter. That is the bending moment at C. Okay. So that completes the examples, that is application of ILD for a simply supported beam subjected to point load, UDL longer than the span and UDL shorter than the span. So that is for today's session. In the next session, we'll take up how to apply this ILD in case of trusses. How to apply this ILD to find the axial forces of a truss member. Thank you.